So we're picking up in chapter 16. So we've done a problem similar to this, where we had a parallel plate capacitor and a charged particle undergoing some displacement. So we had to find the work done, find the speed of the particle, and then find the potential difference through which the particle moves. So this is a similar situation, but something strange is happening here in part B. So I'm going to spend a good bit of time discussing that part of the problem, because something different is happening here involving the displacement of the electron. So the electron is initially at rest, and it's at position 2 inside the capacitor. Now the width of the capacitor is 3.5 millimeters. So I've got a couple length markings here. So position 2 is 3 millimeters from the negative plate. So that means it's 0.5 millimeters from the positive plate. And then there's a second position that's referred to position 1 that is 1 millimeter from the negative plate. So that means it's 2.5 millimeters from the positive plate. So we've got some distances marked, and we've got the width of the capacitor in the problem. It says the magnitude of the electric field is 730 newtons per coulomb. So the first part is drawing the electric field lines inside the capacitor. So I have to indicate the direction of the electric field. The electric field always goes away from the positive plate and towards the negative plate. So my drawing looks like this. So I drew a couple light lines inside so I didn't mess up my diagram too much. But the E field is pointing in the negative x direction. So the electric field is negative 730 newtons per coulomb in the x direction. So the problem says, part B says, what is the work done to move the electron to position 1 from position 2? Now the question here is, what is the work done? And work done by what? So I'm looking at this problem and I see that there's an electron that's moving towards the negative plate. So that tells me that there's something else other than the parallel plate system that's doing work. If I let go of the electron here at point 2, the system would do work and it would displace the electron towards the positive plate. Alright, the electron is going to go against the electric field and it's going to travel to the right. But something's causing it to move to position 1 from position 2. Right? So it's actually going against the force that it would be experiencing due to just the system. So there's some external agent at work that's causing the electron to go towards the negative plate. So I'm going to use my expression for the work done. The displacement of the particle is in the negative x direction. So the displacement is negative, the charge is negative, and the electric field is also negative. So if I use work as QE delta x, I actually get negative work. Alright, so I plug my values in and I get negative work. Now what this means is the negative sign tells me that this is the work that's being done by the plates. Okay? So this is kind of like going back to our gravity analogy. If I pick something up off of the ground, I'm doing positive work because I'm applying a force in the direction of the displacement. Okay, displacement is in the positive y direction, my force is in the positive y direction. Simultaneously, the Earth is doing negative work on that object because the force is in the opposite direction of the displacement. So in this case, the force that the system is applying on the electron is in the opposite direction of the displacement. So that's why we're getting negative work. But the agent that's causing the system to move opposite the system's force is some external agent. So there's some work being done against the system that's causing it to move in the negative x direction. So this negative sign is the work done by the plates. Okay, so the system itself is doing negative work where some external agent is doing like positive work. So the moral of the story is that the potential energy of this particle is actually increasing. So it's very similar to an external agent lifting an object above the Earth's surface. Okay, so there's positive work being done by some external agent, but there's negative work being done by the system. Okay, and my notes could be a little clearer on that. I think it's the external agent that's doing positive work, causing an increase in potential, but it's the system, it's the two-plate system that's doing negative work, which is causing an increase in potential energy, because work is negative delta U. So we're going from position 2 to position 1, right, which is in the direction of the electric field, but we're talking about a negative charge, right? So there has to be some external agent applying a force on this electron in the negative x direction. So it goes against the force that's being applied by the two plates. So part C says, through what potential difference does the electron move? Again, when we're talking about potential difference, we're talking about voltage, right? So we're talking about a change in electric potential from some position to another. Okay, so we're talking about a delta V, and that's independent of the charge itself, right? It's independent of the sign of the charge, any other properties of that particle, right? We're looking for a potential difference, we're looking for a voltage, a change in the potential energy field. So again, I've got a couple different ways I could do this, right? I could use delta U over Q, which is negative work over Q. I could also use E delta X, or negative E delta X, right? So I could use either one of these expressions to solve for C, as long as I took delta X to be the displacement of that particle, right? So just like the previous problem, I showed you two different ways, right? We could use delta U over Q. Since I know the work, I know the change in potential is just negative the work. I could also use, if I knew the particle's displacement and the magnitude of the electric field, I could use negative E delta X, and I would get the same value, or something very close, you know, if I rounded differently or something like that. So I decided to use delta U over Q in this case because I already had the work done from the first part. This is the work done, the negative work is the work done by the system, which is what I'm concerned with here. So the voltage, or the change in potential, is negative work over the charge. So since work is negative, these two negative signs are going to cancel out, but I have a negative sign for my charge because it's an electron. So I end up with a negative value for potential, which is negative 2.2 volts. Now if I go back to my diagram, and if I disregard the fact that there's an electron going from right to left, this location, this area is a high potential, right? We've got positive charge, there's a high potential here. This plate is a low potential. So this particle is actually moving from position 2 to position 1. So it's moving from a high potential to a low potential. Again, just like the previous problem, even though the potential energy of that particular charge is increasing, it's an electron, it's moving from a high potential position to a low potential position. So we're actually getting a delta V of negative 2.2 volts because the particle is moving from a high potential position to a low potential position. Okay, another one of those backwards issues that we have with this electron. Even though the potential energy of the particle is increasing, it's moving from a high V to a low V, which again makes sense because it's moving in the direction of the electric field, and E is negative delta V over delta X. So the electric field is always pointing in the direction of a decreasing potential. Okay, so that makes sense physically. The electron's moving in the direction of the electric field due to some external agent pushing it in that direction. So even though its potential energy is increasing, it's moving from a high V to a low V. High potential to low potential. So part D asks, what is the potential difference across the capacitor plates? Again, this is independent of the charge's displacement. This is just referencing the voltage or the potential difference between two positions. Now I'm going to use, instead of using this expression, I'm going to use the magnitude of the electric field times the distance between the two plates. So I'm using 3.5 times 10 to the negative 3 meters for delta x. Not the displacement of the particle, but the actual distance between the two plates. So I use negative E delta x. The electric field is in the negative x direction. Don't forget this negative sign. And I have 3.5 times 10 to the negative 3 meters. Now I have this little note here. Is it positive or negative? So I'm going to say it's positive right now. So the potential difference between the plates is 2.6 volts. I could just as easily say that this is negative 2.6 volts. And why is that? Because this potential at this location is high. The potential at this location is low. So if I said V final minus V initial, so if I took the positive plate to be my V final minus V initial, I'd have a high potential to a low potential, so I'd have a positive voltage. And that's what I did in this example. I said, this is my final position, this is my initial position. Right? So this is positive 3.5 millimeters, this is 0 millimeters. So that gave me a positive delta x, which gave me a positive voltage. If I switched my coordinate system and I said this was 0 millimeters and this was negative 3.5 millimeters, my delta x would be negative. And that's okay. There would be a negative potential across the plates. So it all depends on your coordinate system and how you define it. My convention usually is I take the high position, or the high voltage position, to be the final, the low voltage position to be the initial. That way I get a positive voltage. Right? If you did this problem and you said this was negative 3.5 millimeters and this was 0, you got a negative potential. That's perfectly acceptable, right? It all just depends on your coordinate system. Okay, but again, my convention is that, I like to have a positive potential difference. So I pick this to be my final, this to be my initial. But again, the difference between parts C and D is that displacement, right? The electron is actually moving through a smaller potential difference strictly because its displacement is smaller than the distance between the plates. If I put an electron here and I let it travel all the way here, I would use the 3.5 millimeter displacement for part C. But it doesn't move across the whole distance between the plates, it just moves from position 2 to position 1. Okay, so watch out for that. The language in the problems, make sure you're using the correct displacement based on what the problem is asking. So try this with some good practice would be take the same problem, same dimensions, and put a positive charge at position 2. Put a positive charge at position 2. Now we know that this positive plate is going to push the proton, right? Let's make it a proton. So put the proton at position 2. We know the positive plate is going to push the proton to position 1. So do the same problem and just replace it with the proton, and then see what happens with the work, right? See what happens with part B, see what happens with part C and D. Okay, and we'll see that you won't need an external agent to push the particle to 1. So the only work that's going to be done on the proton is going to be the work due to the system. Okay, so give that a try, do the same problem, and just put a proton here and see how that changes. So much like our gravity analogy, we don't always deal with lines or plates of charge. Sometimes we have point charges that are interacting via the Coulomb force. But just like two particles that are massive exerting gravitational forces on each other, there's a potential energy of this system, this two-charge system. Now in experiment 5, if you're in the lab, experiment 5 will be dealing with these 2-point charges. This is what we call a dipole. So if you have two oppositely charged point charges some distance from each other, we call this a dipole. So the potential energy of this system, if we go back to our gravity analogy, we've got a potential energy of the system that's directly proportional to the charges, and it's inversely proportional to the distance between them. Now, the issue with this is we don't have our magnitudes, right? We don't have those absolute value bars anymore. So the potential energy of the system, even though it's a scalar, it's not a vector, it's an energy term, it's a scalar, it can be positive or negative depending upon the sign of the charges, right? So if these charges are the same sign, then the potential would be positive, right? So if you have two positive charges or two negative charges, the potential energy of the system is going to be positive. So what does that mean? If you let go of those two charges, right? If those two charges were close to each other and they were the same charges, they would repel each other, right? So there's positive potential. So if you let go of that system, there's potential energy stored in that system, which would be transformed to the kinetic energy of the charged particles, right? So they would repel each other and they would go in opposite directions. So if the charges were opposite, like in this diagram, the potential energy would be negative, right? You would actually have to do work to keep them apart from each other, right? So the potential energy of the system is negative. If you let go of that system, those two charges would be attracted to each other. Okay, so even though potential energy is a scalar, right? We don't have these absolute value bars anymore. It depends upon the sign of the two charges. All right, so I see that happen a lot. We're going to a new chapter, right? Chapter 15 was dealing with vectors, forces and fields, and we were dealing and we used Coulomb's law to find the magnitude of the force between these two charges. Now we're dealing with scalars, but just like work and potential energy, it can be negative. Okay, so watch out for that. And again, this isn't an inverse square law. Okay, when I did that derivation, that squared went away. Okay, so this isn't squared, and we don't have the absolute value bars. All right, so just be careful with that. So how do I get this potential energy close to zero? The farther apart these particles are, the closer that potential energy of the system is equal to zero, right? If you divide something by infinity, which technically you're not doing, but as r approaches infinity, this term is going to approach zero. So this is the potential energy of a multiple charge system, right? We're talking about the potential energy of that system. But if I got rid of one of those charges, much like electric field, if I got rid of one of those charges, there would still be a potential field at some location due to this single charge. And that's what we're talking about when we talk about potential difference and voltage. So we're talking about the electric potential and the value of the electric potential field at some location, regardless of whether there's another charge there. Okay, and as we compare two positions, right? Let's say this position to this position, we are looking at a change in potential, right? Or a voltage. We're looking at a change in potential. So I can take that Q2 that was here, right? Let's say that was a negative charge, and instead of potential energy, I want potential energy per unit charge. So I want U over Q2. I want the potential at that location even though that charge is gone. So I divide both sides. I divide this term, both sides of this equation, by Q2, and I get my potential. I get my electric potential, which is K Q1 over the distance between that charge and that location. Just like my gravitational potential at the beginning of this chapter, it's only dependent upon the charge of this particle right here. It's got nothing to do with what's here. It's just the value of the potential field at that location. V is also a scalar, so this is a scalar field, right? So it doesn't have direction, but it could be positive or negative. Notice, it's a positive potential here because I have a positive charge. If this was a negative charge, my potential would be negative. My potential would be negative here. Okay. So again, we're talking about potential energy being 0 at some location infinitely far away, right? R sub 1, 2 would be the distance between that charge and that point. The farther this point is away from this charge, the smaller the potential is. So it's our reference frame is saying potential is 0 when you're infinitely far away from this charge. So let's just do a couple exercises dealing with a multiple point charge system. So this is what you'll see in WebAssign is pretty common. You'll have a configuration of point particles, and you'll be asked for two things. So you're going to calculate the electric potential V at some location, and then they'll say, we'll put a charge there, and then state what the potential energy of the system is. Alright, so in this example, we're looking at calculating the electric potential at the top of the triangle, so this point right here. I've got a positive 2 nanocoulomb charge here and a negative 1 nanocoulomb charge at this location. So there's going to be a positive potential due to the 2 nanocoulomb charge here and a negative potential due to the 1 nanocoulomb charge here. So since potential is a scalar, I'm just going to calculate the potential at that location due to each individual charge, and then just add them up, and I'll get the net electric potential at that location. The second part of the problem is to calculate the potential energy if we place a 1 nanocoulomb charge at that location. So that'll be a nice, pretty straightforward second step. Once you calculate the potential, it will be one quick step to find the potential energy. Just like in chapter 15, I could calculate the electric field at some location, and then, you know, part 2 of that problem could be, alright, now put a 5 nanocoulomb charge there and calculate the force, right, which is just the electric field times the charge. And so we'll do something similar in this example. So I'm going to first I'm going to calculate the potential at these due to these two charges. It's a scalar, but again, we drop the absolute value bars. The potential at some location is due to the sign of the charge, right? So it's sign dependent. So the potential due to the 2 nanocoulomb charge is K times Q2 divided by the distance between that charge and the location. Again, it's not an inverse square law. Alright, one of those R terms went away, and we don't have the absolute value bars. So we plug our value in for K, plug our value in for the charge. Here's one thing I noticed that will kind of make our lives easier. You notice a lot of times it's Coulomb's constant times 1 charge, or times the product of 2 charges. Coulomb's constant is on the order of 10 to the 9, and if we're dealing with nanocoulombs, this 10 to the 9 and this 10 to the negative 9 cancel. Alright, so just a little quick step, maybe make our lives easier, help us avoid calculation errors. So this 10 to the negative 9 and this 10 to the negative 9 cancel. So actually my numerator is just 9 times 2. So it's 18 divided by 5 times 10 to the negative 2 meters. Again, not squared. So we have a potential of 360 joules per coulomb, or 360 volts at that location. But that's just due to the 2 nanocoulomb charge. So I've got to calculate the potential due to the -1 nanocoulomb charge. And so again, it's a scalar, but potential can be negative. It's dependent upon the sign of the charge, so we don't use our absolute value bars here. So K times Q -1, which is 1 nanocoulomb, divided by the distance between the 1 nanocoulomb charge and that point, which is 4 centimeters. Don't forget to convert your distances to meters. And we have a -225 volts. So calculating the net potential at that location, I'm just adding these two scalars up. So 360 minus 225 volts gives me a net potential at that location of 135 volts. So now the second part says put a positive 1 nanocoulomb charge there and then find the potential energy of the system. Okay. So we've got our relationship between force and field. We also have our relationship between potential energy and potential. Okay. So I don't have to do this, right? I don't have to do this twice for the 2 nanocoulomb charge and the -1 nanocoulomb charge. And once I have the potential at some location, I can just take that potential and multiply it by the charge that I'm placing there, right? So if I multiply both sides of this by Q2, I get delta U is equal to delta V times Q2. And that Q2 is the charge that I'm putting at that location. So all I have to do is take the potential, the voltage there, multiply it by the charge I'm placing there, and I get the potential energy. So that's what I'm doing here. I already have the net potential at that location, multiply it by the charge. A volt is a joule per coulomb, so joules per coulomb times coulombs is joules. So I have an energy value here. So a positive 1 nanocoulomb charge times the potential at that location, I get 1.35 times 10 to the -7 joules. So we'll do another problem, very similar. We just we add an extra charge. This diagram should look pretty familiar to you, but instead of dealing with forces and fields, I'm dealing with the potential at this location. So this is a typo right here, so I'll clean that up. I'm actually looking for the potential here in the top left corner of the rectangle. Alright, so I'm going to calculate the potential due to the 6 nanocoulomb charge, the positive 5 nanocoulomb charge, and the -3 nanocoulomb charge. So again, they're scalars. I'm going to have a positive potential due to these two, a negative potential due to that, and then I'm going to calculate them and just add them up. So the potential due to the 6 nanocoulomb charge is KQ6 over R6. So I know Coulomb's constant. I know the magnitude of the 6 nanocoulomb charge, and the distance between the 6 nanocoulomb charge and that location is 0.6 meters. Again, we're dealing with potential. It's not an inverse square law, so I'm not going to square this R. So I get 90 volts. I get 90 volts due to the 6 nanocoulomb charge. The positive 5 nanocoulomb charge, if we go back to chapter 15, we use the distance is the diagonal of this rectangle, and so I use the Pythagorean theorem. 0.6 squared plus 0.2 squared is the length of this diagonal squared, and so when I use the Pythagorean theorem, I find that this distance is 0.63 meters, just like our chapter 5 example. So I know K, I know Q5, which is 5 nanocoulombs, positive. It's a positive charge, and I get a potential of 71.4 volts due to that 5 nanocoulomb charge. Finally, I've got the potential due to the -3 nanocoulomb charge. This charge is 0.2 meters from that location. Alright, so 0.2 meters is the distance I'm using for R3. Plug in K, plug in -3 nanocoulombs. We're dealing with the potential, which is a scalar, but it depends on the sign of the charge. So -3 nanocoulombs, when I calculate this, I get a potential of -135 volts. So I add them up together, 90 plus 71.4 minus 135, and I get a net potential at that location of 26.4 volts. Second part of the problem, put a charge at that location, multiply it by the potential, and then I have the potential energy of the system at that location. So I get 2.64 times 10 to the negative 8 joules. So for a little bit of practice, maybe go back to chapter 15. Let's pull up our chapter 15. Pull up our chapter 15 PowerPoint and just look for a couple situations where we can apply the concepts of potential and electric potential energy. This triangle is really nice. WebAssign, you'll have some charge configurations and stuff. So pick a point, right? Maybe take that 2 microcoulomb charge out of the configuration and calculate the potential field at that location due to these 2 charges. Calculate the potential at that location, and then bring that 2 microcoulomb charge back and calculate the potential energy of the system. Right? And you can do this for each one. Right? Take the negative 4 microcoulomb charge out, do the same thing. Take the 7 nanocoulomb charge out, or microcoulomb charge out, do the same thing. Pick a point right here. The center of the triangle's base. Right? That would be a good one. So that's 0.5. This would be 0.25, right? Use the Pythagorean theorem, get that distance. So pick a point right in the middle between these 2 charges, calculate the potential, and then put a charge there of whatever magnitude, whatever sign you want, and calculate the potential energy. So that would be good practice for the potential of a point charge system. Okay, so that wraps up chapter 16. Again, if you have any questions on your homework or these examples or anything, send me an email. We can talk via email or Zoom, whatever you want to do. We can set up a time. So have fun, practice the problems, and I'll send some announcements out. Our exam is on Friday, so it'll be on chapters 15 and 16. So I'll send some announcements out through D2L. Be on the lookout for those announcements. All right, thanks.